All right. Thank you all for joining us. I'm very, very honored to introduce Nikhil Naik. He's just finishing his PhD at the MIT Media Lab, and then we're very excited he'll be joining Harvard as a fellow in the Prize Fellowship in Economics, History, and Politics. He is, yes, exactly. Incoming postdoc. So if you're excited by what you see today, you can talk to him and pitch ideas. He is truly incredible. So he does tier 1 work in machine learning and computer vision, and one day decided he also wanted to take that work and apply it to social science. And so he's now revolutionizing urban science on a whole bunch of different dimensions, using computer vision tools to do the types of studies that we used to do by foot or by hand at massive, massive scale. It's been my extraordinary honor to be his co-author on one of these ventures, but he's the linchpin and the center of this entire program, and it's absolutely wonderful to have him here. So, QED.
Thank you for the very kind words, Scott. You can always count on Scott to make a great introduction. As he mentioned, this is our work on applying techniques in computer vision and machine learning to sort of urban science. So that's why I titled my talk Visual Urban Sensing. And this is a joint work with my co-authors, my advisor Ramesh Raskar, Cesar Hidalgo at the Media Lab, and Ed Glazer at Harvard Economics, and of course Scott here. And we'd like to thank our sponsors, various companies, and Google and NSF. So it's no secret that the world is undergoing rapid urbanization. According to some estimates, more than 5 billion people will live in cities by year 2025. And perhaps more importantly, about 4 billion of them will be living in developing countries in cities. And this is sort of unprecedented, and there are several interesting questions in urban science at the intersection of economics, urban planning, computer science, which can help improve this process and help us learn more about cities. So in this talk, I'm specifically going to focus on developing a set of measurement tools for urban science and demonstrating that they're useful for studying different questions. So specifically, I'm going to focus on tools that evaluate urban appearance along different dimensions. And by urban appearance, I mean that what can you understand by looking at how cities look and extract information from them. So there's a variety of things that you can obtain from just the visual appearance of cities. You can look at the quality of built infrastructure. You can measure their perception. You can see how clean they look, how safe they look, how lively they look. You can also infer metrics like population density, socioeconomic status, property evaluations, and so on. And finally, you can also try to get a sense for the quality of life metrics in these places. And you can do these studies both at cross-sectional level and longitudinal level. And this data is useful for a wide variety of fields, including urban economics, urban planning, sociology, and so on. So I'm going to sort of talk about two problems which can be studied using this data. So the data on urban appearance can be used to study questions on measuring the impact of urban appearance on behavior and health of its citizens. And secondly, you can use cross-sectional data, longitudinal data, to understand the causes and consequences of changes in cities. So how are these questions studied right now? At the moment, economists, sociologists, urban planners, and other social scientists typically use census and government records to study these questions. This data is typically non-uniform in spatio-temporal resolution, and it's hard to access sometimes. Especially, it's hard to access this kind of data in developing countries. Secondly, they conduct surveys and field studies of cities to collect this data. These surveys are time-consuming, and they can only cover so much space. So to give you an example, the Great American City Project out of University of Chicago, which sort of evaluated the appearance of cities across neighborhoods across Chicago, took a decade to complete. But interestingly, a new source of data on the visual appearance of cities has emerged in the last decade, and that's Google Street View. Street View cars have driven around the world and collected these panoramic photographs of cities. So we now have data. So the regions in blue here, they show the parts of the world where this data is available. So more than 3,000 cities from 100 countries across the world have been photographed at the street level. This data is high resolution, it's available publicly, and it's amenable to analysis both by humans and by computers. And interestingly, also time series data is available starting from 2008. So we have imagery of locations every few months or every few years for places across the world. So sort of this advent of Google Street View has been paralleled by great advances in computer vision. So the technology of analyzing images and videos has made impressive gains in the last half decade, specifically fueled by advances in deep learning and neural networks. So which means that now we have sort of an opportunity to develop automated surveys of the built environment at unprecedented resolution and scale. We can use these computer vision techniques in combination with crowdsourcing and human input to conduct large-scale surveys of cities. So the first problem I'm going to focus on is evaluating the impact of physical appearance of cities on human behavior. So there have been all these theories on how physical appearance of cities impacts crime, health, education, and mobility of its residents. And several studies have been undertaken in social science to understand this relationship. So to give an example, the famous broken windows theory proposed in the 80s by Wilson and Schelling says that a neighborhood that has urban disorder and vandalism, like broken windows and graffiti, leads to additional crime and antisocial behavior. And this theory has been used as support for various government initiatives to clean up cities and to improve neighborhood appearance. And again, the sort of the evidence for this is mixed. It's unclear yet if this theory is really useful or not. So if I were a social scientist, if I were to study this theory, what I would do is I would probably go out and conduct a field study, a field survey. I would send someone out to neighborhoods, try to measure appearance, or I would send out a survey to residents to try to measure how they feel, how they perceive their own neighborhood. But it can only cover so many places. So to sort of automate this data measurement, we created this online tool called PlacePulse in 2013. So it's a crowdsourced online game where we show people pictures from Google Street View side by side, and we ask them questions like which place looks safer. So people could come and click on an image and tell us which place they feel looks safer. And this game ran for about 8 months, and we had some online publicity. We did Facebook advertising, and more than 8,000 participants from 90 countries came and clicked on these images from New York and Boston and 2 cities in Austria. So we collected more than 200,000 comparisons or clicks from these participants. Now that we had these clicks, we want to convert them to rank scores, to rank images based on their perception of safety. So we use this Microsoft TrueScale algorithm, which is a Bayesian algorithm for converting pairwise comparisons to rank scores, and it's typically used in online games. So the idea there is that you model each player's or each image's score as a Gaussian variable with some mean and sigma, and that gets updated after every comparison. And this algorithm converges after about 20 to 30 comparisons to give you stable ranked scores. So now you have an absolute number for each image. So here are some examples of images with a low street score. We call the score of perception of safety street score. And as you can see, empty streets and warehouses and and so on appear unsafe, while busy streets and townhouses and suburban houses, they appear safer. We also did some experiments to test different. Yes.
Did you do anything to characterize people doing the ranking? So, for instance, you showed like basically Northeast U.S. and Austria.
Sure.
And if everybody that was doing was like white and male, wouldn't they be biased to, for instance, find places that were safer that looked like places they live?
So our participants came from all over the world, and we did demographic studies, which I'll cover next. Yes?
Quick question on the ratings as well. How do you control for the weather? So for example, maybe cloudy, rainy days look more unsafe than bright, sunny days.
So we showed images just for the summer, and there were, of course, some images which had cloudy, rainy pictures and so on, but that didn't have much of an effect based on our analysis, which I'll show later. And the reason we had pictures from Austria and stuff because we want to do some Photoshop-based studies, and you can't do that with Google Street View. That's why these two sort of seemingly unknown cities from Austria. Yes?
How well correlated are these rankings with the actual statistics on?
Yes, that will come next as well. So here are some results from our Photoshop studies. So what we did is that we placed some objects in the picture using Photoshop. So here looking at, we have placed some trash on the ground, and this is the actual picture without trash. And we compared how are people's perception affected just by placing some trash on the ground. As you can see here, as you can see here, the perception of a place without trash goes up significantly as compared to the place with trash. In another example, we had this road, we had the street with a road, and then here's some tar patches on the road. And if you look at how the place to compare, again, just by removing the tar patches and resurfacing, the score goes up significantly. Here's a final example. So we had the street where you have these overhead wires, probably for a tram or a streetcar, and by removing it, we can remove it. And again, the score goes up significantly just by removing these ugly-looking wires. So this kind of experiments can help us sort of understand how different visual elements are affecting people's perception. And some of you might have noticed that when we removed the wires, now we have a traffic light hanging in midair magically, but people don't seem to care about it as much. So to answer your question about sort of demographic bias, we did collect data on age, gender, and location of the users. So we were able to look at sort of a control group and the group with, so we compared people who were older versus younger, male versus female, non-US versus US, and we found that there was no significant statistical difference in their perception, at least for the images in our set. But again, so this survey was quite limited, as you can imagine. This is a picture of New York with the red dots overlaid, which show that how many street blocks were sampled, and clearly we can't really sample many street blocks. Out of 1 million street blocks, we only able to sample 1,700 street blocks. To really scale this up, we need to use automated techniques. We need to use computer vision to be able to automatically score images. So we draw on techniques in computer vision which try to predict sort of these non-semantic attributes like aesthetics, memorability, and so on of images to create a method that can do this. So just to give a very brief overview, we start with an image and we perform so-called semantic segmentation on the image. So we assign essentially a label to each pixel based on which category of object that pixel belongs to. So in our case, we chose to keep it simple. We only chose 4 categories. So each pixel is assigned a label out of sky, building, ground, and trees. After we do that, we sort of extract these image features from these regions. So we extract features that roughly encode the shapes, textures, and colors that are present in the image pixels of each of these categories. So we now have a feature vector that has shapes, textures, colors for these 3 different categories. Then we can use a support vector machine. We can use a support vector regression algorithm to use the data, to use the feature vectors and their labels for street score or perceived safety to train a method. So it does quite well on the training set. As you can see here on the test set, we have about an R-square of 0.4 between the true and predicted scores. So on the x-axis, you're looking at the true street scores, and the y-axis, you're looking at the predicted scores in the scatter plot, and there's a pretty good fit between the true and predicted scores. Again, we can use the advance in machine learning to improve the performance. So we can use neural networks, and we can improve the R-square to about 0.72. So we can get a better prediction. So since we trained the algorithm using a linear predictor, using a regression algorithm, we can look at the contributions of different elements that make up our feature vector. So we can look at how much do buildings contribute to the perception, how much does the sky contribute, and so on. So what you're looking at here is you're looking at the scores overlaid on top of these categories with these plus minus numbers. So what they're showing is how much does this building contribute in comparison to the average building in the data set. What it's showing is this sort of nice house increases your score about 0.5 points, versus that which looked like a warehouse reduces your score by about 0.5. So we can do this kind of analysis to look at how different architectural styles, different types of buildings, different types of streets, and so on are affecting your perception. This is sort of a summary result based on that analysis. So what you're plotting here is different types of buildings and trees and so on, landscaping, ground, the streets, and we're looking at their contribution. So you can see that, for example, unpaved roads reduce your perception of safety, while roads in good shape with sidewalks increase the perception of safety. Similarly, with different types of buildings, as we go from warehouses and so on to fancy office buildings, apartment buildings, the score goes up. So we can do this kind of analysis. And again, to answer your point about weather, roughly we look at different types of sky, and there is not much contribution of the weather in itself to the perception. So anyway, now that we have this predictor, we can go to Google Street View, we can scrape several 100,000 pictures, and we can score them based on perception of safety. So on the right, you're looking at a map that's scored by our algorithm with regions showing in red and green based on your perception. This is available publicly on our website, Streetscore. So you can go to the URL and you can click at any location, and it will show the picture and its perception as scored by our algorithm. And because we have the advantage of scale, we can go and score several cities. So on our website, we have different cities ranked at the same resolution. So in fact, we tested the algorithm on several cities in the US, and we created this data set which has more than 1 million street blocks, and it's available publicly as well for all these different cities. So since we released the data set about 2 years ago, several researchers have been using it for sort of studying these different questions on how urban appearance affects people. So there have been work on how the policy and how urban planning constructs affect urban appearance. There's been work on historic preservation districts. Then there's been work on sort of education programs. There's some work on urban upkeep, social cohesion, and so on. Some work on mobility in the sense that how does perception affect mobility of people based on cell phone records. And we have done some work on actual crime. So how does perceived safety relate to actual physical crime? So I'll sort of go briefly over how does this perception or street score relates to demographic. So we collected this data on street score for different cities, and we computed different metrics for the street score at census tract level. So the idea is to aggregate these metrics at the level of a census tract and see how the perception of safety is correlated to actual demographic data. So we collected data on the mean street score, on the standard deviation of it, and the Moran's I. The Moran's I essentially calculates the spatial autocorrelation. So it calculates how is the perception of safety segregated. Do you have neighborhoods that have sharp boundaries between perceived safe and unsafe neighborhoods? And then we can run multivariate regressions. These are all spatial multivariate regressions with controls for city fixed effects. And we are looking at how are different variables correlated with the perception. And as you can see here, there is pretty high correlation with density, so high correlation with population, low with area, so high correlation with density, then high correlation with higher age, higher education. Then interestingly, the standard deviation has high correlation with Gini index, so more income inequality, more also inequality in the perception of that place. And for example, we have high negative correlation with these sort of large housing projects as reported by the census. So you can start to look at patterns of how does the physical infrastructure relate to the demographic of people who live there. This also enables us to do analysis on crime, which is sort of the main question we started with, is that how does the perception of safety affect crime? So we collected data for about 19 cities, and we aggregated at census tract level. So we had data for thefts and burglaries and violent crime for all these cities across the US, and we were able to correlate the perception variables, the perceived safety variables to crime variables. So this first regression, which doesn't have any perceived safety variables, it only has the demographic variables. And so in this case, I'm showing you the correlation of theft with all the demographic variables. And in sort of in tune with previous research in criminology, we find that there is high correlation with population, sort of very strong negative correlation with age, younger people committing more crime, high correlation with income inequality, and so on. So that's just based on demographic, and that's sort of confirming the previous trends in academic research. And when you add these perceived safety variables, we find something interesting. We don't find that there is high correlation with the average level of safety. So you would expect that there is a high negative correlation with average perceived safety. So the more unsafe the neighborhood looks, more the crime. But that's not really the case. We have a pretty weak effect for the mean street score. But interestingly, we have very strong positive effects for the moron's eye and similar but smaller effect for the standard deviation. So what it's saying is that after controlling for all demographic variables, if your neighborhood has a pretty high segregation in perceived safety, so in safer, unsafe looking neighborhoods, then you are getting more crime. And we find that this strong and significant effect persists across burglaries and violent crime, including murder and so on. So this is a pretty surprising finding for us, and it's still a work in progress, but we are working on a paper when we are trying to explore. Yes?
So are those crimes distributed across both the safe and unsafe looking areas, or are they mostly in one of those areas?
Right, so has been a bit tricky question to answer because a lot of our crime data has been reported at the police station. So essentially, we don't have fine-grained lat longs. So that's something we have been working on, try to get more data and to try to answer this better. But they are indeed in that census tract, but it's a bit trickier to understand the spatial distribution at the moment. Mm-hmm. That's why I put the work in progress here. We're still trying to figure out what would be some reasons for this. But it's indeed finding that's not been found before, and it's something that's looking at how the physical infrastructure is affecting crime. So moving on, so what I presented so far is sort of a method that can look at the perceived safety of neighborhoods and that can do it in automated fashion using computer vision techniques. And this has been found useful for different researchers who are studying the impact of urban appearance on the behavior and health of its residents. As you may remember, the data for our algorithm came from New York and Boston mostly. And as a result, the algorithm does not do as well in other parts of the country. So essentially what we found is that if you try to apply the algorithm that's trained using data from New York and Boston on the American West Coast, it does not do as well because the visual appearance is quite different in other parts of the country as compared to New York and Boston, which is expected. So to sort of try to expand the geographical coverage of our method, we started a new survey a couple of years ago, and we created to create a global data set of urban appearance. So similar to our first method, we created a much larger data set which had about 100,000 images from 56 cities across all continents. So now we had all these images taken from Asia, from America, Europe, and so on. And similar to the first study, we ran this online game. And we asked people several questions, including about perception of safety, liveliness, wealth, beauty, etc. And we had about 100,000 images. So again, in about 2 years, we collected more than 1.3 million clicks or comparisons from 80,000 people. For some reason, people love playing this game. We keep getting clicks from different people without really using something like Amazon Mechanical Turk or so on. But the problem here is, though, that we can't really get enough number of clicks per image as the previous survey to be able to get reliable true skill rankings. So we are not able to get stable scores by converting these pairwise comparisons to rankings since we don't have enough clicks for the algorithm to statistically converge. So the solution we decided was to, instead of using a ranking method, in between, we should just train a neural network to predict these pairwise comparisons and to be able to generate synthetic comparisons. So the idea is to feed a neural network these pairwise comparisons and the human decision to be able to then, for a neural network to predict the comparisons on its own. So we created this neural network architecture where we feed it these two images and a decision based on the human ranking, and the algorithm is able to, the network is able to train with a joint classification and ranking loss. So it's trying to both maximize for how many clicks it gets right and how many, and also it sort of gets the global distribution of rankings correct. So it's trained using these 1.3 million comparisons, and it's able to do quite well. So as you can see here, based on one network topology, we can get about 73% accuracy for predicting the pairwise comparisons for the perception of safety. And we can do this for all attributes. And so we had about 6 attributes in our data set, including safe, lively, beautiful, and so on. And the prediction performance sort of gets worse as we have less and less data for different attributes, but in general it can do pretty decently based on if you have enough data for a given attribute. So now that we have this neural network, we can feed it random image pairs and get decisions based on the neural network, and then we can feed it to a ranking method like TrueScale to now get absolute ranked scores if we want to visualize the data or if we want to aggregate it. So here are some examples where we are showing you different attributes, including safety, liveliness, beauty, and so on. And as you can see, as you go from low to high, the perceived safety or beauty goes on increasing. And these are created based on the clicks generated by neural network. Because we now have the neural network, we have scored more than 10 million images for about 100 cities in the world, and we are releasing this data set soon publicly, so people can from across the world can use this for different studies. So far I've told you about the perception of places and how it can be used to study different questions, but now I'm sort of going to move on to studies using longitudinal data. Because cities are not static, cities are changing all the time, and this is sort of the most famous example probably where you have Shanghai in 1990 in China, and it's been completely transformed in about 20 years to how it looks now. So cities are changing dynamically, and it's important to, again, collect data on the visual appearance of cities and how they are changing. And this data could be used for studying demographics and public goods, urban policy, and how all these other elements are affecting change in cities. And the reason we can do that is that we have, again, this data source from Google Street View called Time Machine, which has collected images across years for these cities, and it's available online. So you can access imagery starting from 2008 for almost every few months. And because we have a method to sort of evaluate the visual appearance of cities, we can use this data to create a metric for change in cities. So just to give an illustration, here is a place in Brooklyn, New York in August 2007, and we can use our Streetscore algorithm to evaluate its perceived safety. And you can see that it scores about 1.8 out of 10 because the place doesn't look that safe. There is sort of construction going on, so the algorithm scores it low. Then we can go to the same location in 2014, and we can scrape the picture from Google Street View, and we can also evaluate it using Streetscore. And as you can see, the place has been completely transformed. There's these nice buildings, people walking on the street. The place has changed completely, and the Streetscore has gone up pretty significantly. So just to show you again, this was the place. This is the place in 2007, and this is 2014. So by just looking at these registered image pairs and evaluating the Streetscore, you can see how much the place has changed. So in other words, we can use Streetscore as a proxy for change in the physical appearance of locations. So we had to modify our algorithm a little bit, but essentially we had to sort of make sure that the algorithm is not affected by season changes, is not affected by things like occlusions and overexposed or blurred photographs, but essentially we're able to clean up the data to retain image pairs which are 7 years apart, and we're able to compute their Streetscore, and the change in Streetscore gives us this urban change coefficient, which is giving you how much the place has changed in this 7-year period. So here's an example where you're looking at a place in New York, and it's a place where there's no significant change happened, and it shows that the algorithm works. So here you have not much change in the built infrastructure, the streets and the buildings, but there's significant change in vegetation and weather, but the algorithm is invariant to that, and it says that it's almost the same place. Not much change has happened. But here's an example where significant positive changes happened. So 2007, 2014, same location, and these new buildings have come up and so on, and the algorithm gives it a significant positive score. Here are some more examples just to show you what kind of things is the algorithm finding. So these are all image pairs where there was a significant positive change. So with varying degrees of change. So it can identify things like renewal, where the building has been improved or changed. It can essentially also identify large changes where you have construction and so on. Here it's showing a new train that's now running and so on. So it's able to identify all different kinds of changes, and it also gives you a number for how much the change the location has experienced. It can also identify decline. So here looking at an example of a place in 2007, 2014. And as you can see, this house has now been torn down, and the sidewalk is now unkept, and so on. And so it's sort of an indication of decline, and the algorithm is able to assign a high negative score indicating decline. Here are some more examples of decline, sadly most of them from Detroit. And you can see a lot of them are basically buildings that are now abandoned, they are torn down, and so on. And so it's essentially able to identify these kind of negative changes as well. So again, now because we have advantage of scale, we can essentially scrape every street block from any city we want to study, and we can calculate urban change at every street block level. So here we are visualizing it. I'm sorry if it's not very bright, but essentially the red spots that you're looking at here are showing the places which experience more than 4 standard deviations of positive change in the last 7 years. And you're looking at usual suspects like Williamsburg in Brooklyn and this area around Highline Park. So if you're familiar with New York, you can figure out that it's essentially identifying all these places which have experienced large growth in the last decade or so. Here's a similar example from Boston. So again, we have these red spots which are showing significant positive change. So area around MIT on 3rd Street, which has experienced a lot of change in the last decade. Oh, that's better. In the last decade, it's showing up in red and so on. So the algorithm does a pretty good job at identifying both growth and decline in cities. So now that we have the algorithm to sort of quantify the change in locations, we used it to answer sort of classical questions in economics on why urban change happens and what are different factors that affect it. So we created a data set from 5 American cities. So we essentially scraped almost every street block from these cities. So we had data from New York, Boston, DC, Baltimore, and so on. And we aggregated the street score and the change in street score at the census tract level. So we had about 2,500 census tracts, and we collected socioeconomic data from the census from 2000. And what we're interested in answering is we want to look at which demographic factors are predictors of future physical urban change. So we looked at a variety of demographic variables, and what we found is I'm going to give you the key results. So now the main things we found is that education and population density were the main predictors of physical growth in neighborhoods in the future. So what you're looking at in this table is the first 3 columns are showing the correlates of just the street score in 2007 with demographic variables. And you can see that there's very high positive correlation with education and density of the street score, and that's what we found earlier as well in a much larger study. But the next table, which is more interesting, that's correlating the change in street score, the urban change coefficient, with the demographic variables. And as you can see in this last column, after controlling for initial street score, there is a very significant positive correlation with both education and density in these 5 cities. So what it's showing is that neighborhoods or census tracts which have highly educated, dense population are the ones that experienced most positive growth in the last decade. We can also test sort of classical theories in urban economics. So one of the things that we studied was this tipping theory of neighborhood change. So what this theory, which was predicted in the 1960s, the theory predicts that the neighborhoods that are already doing well, they continue doing much better, and neighborhoods that are not doing so well, they sort of go into a spiral of decline. So that's the theory that was presented in the 60s. So we can study the theory by looking at the initial street score, the initial physical appearance of the place, and we can look at how much change did the neighborhood undergo in the last 10 years and 7 years. And so you're sort of looking at these binned plots of initial street score and how much change they experienced. And again, what we see is that in tune with what the theory predicts, neighborhoods that already were doing well, they appear to have the most physical growth based on our data. But we don't find that neighborhoods that were doing bad are doing worse. We find that they still experience a small positive growth in our data set.
Clarification question?
Yes.
Your street score was out of 10, but you've got scores above 10?
Oops, sorry. Yeah. So in this study, they were normalized in the previous data set. In this data set, they were out of 25 because we made some changes on the score. Yeah. So that's why and this is averaged at the census tract level, but they're out of 25 in this study. Mm-hmm. We also study the invasion theory of neighborhood change. So the invasion theory predicts that if you have neighborhoods that are doing well, then that effect sort of spills over in the surrounding neighborhoods, and also neighborhoods that have good location, that are close to downtown, are the ones that experience growth in future. And that was predicted way back in 1920s. And we are also able to test this theory. So what we do is we run regressions of the street score change with variables including distance to the downtown, distance to CBD, and also the average street score of adjacent neighborhoods, the average population density of surrounding neighborhoods, and average college education of surrounding neighborhoods. And again, what we find is that there is a significant negative correlation with distance to CBD, meaning that the closer these neighborhoods were downtown, the more growth they experienced. And we also found high positive correlation with education and population density of surrounding neighborhoods. So again, if the surrounding neighborhoods had high population density and education, that neighborhood experienced more physical growth in our data set. So if we have to summarize all the results that we found based on this data, we can say that we found that basically positive urban change occurs in geographically and physically attractive areas which have a concentration of educated population. And that's sort of illustrated in this map of Brooklyn. So what you're looking at here is the first and second plot. We are showing the density and education of a neighborhood. And in the third figure, we are showing the street score levels in 2007. And the fourth one, looking at the street score in 2014. And as you can see, significant gains were made in places which had high density and high education of the population. So essentially, we have a tool that can measure change in cities at very fine grain at every street block level, and that's sort of much more fine grain as compared to, say, census data, and we're able to test different theories. Yes?
Yeah, I'm just wondering if you, some extent, when you train your model with recent data, right?
Sure.
And is some of the progress not done with just things looking old? And in 2007, it may have been fine, but as your model has been trained with something more recent, because it's look old, people will say, no, they look less safe because it's looked like, nearly 10 years ago. You get what I mean?
So our training data came from 2007, 2009. So it was actually from older imagery itself. So I don't think that effect's happening here. Cool. So sort of to summarize what I presented, we have these measurement techniques for evaluating the appearance of neighborhoods, which are based on crowdsourcing and computer vision, and we can make use of the scale and magnitude of data available from Google Street View to develop these tools for studying cities. We can look at the perception of cities. We can also look at the change in cities, and this data is useful for people who are studying the relationship of urban appearance and change to human behavior, to urban policies, and so on. And while sort of I have focused in this talk on mostly on perception, how people perceive cities, we can also infer sort of quantitative metrics based on imagery as well. So we can infer things like income or property valuations, and we are doing some initial work in developing countries where we are trying to predict socioeconomic status at the street block level based on street view data. So similar to techniques which try to predict things like income from satellite imagery, we can predict income at the street block level from different cities, and that's especially valuable in cities in developing countries where we hardly have any data available on income and other socioeconomic indicators. Thank you. And happy to take questions. Yes?
Have you found any things that disprove any theories? I mean, a lot of theories that you confirm were things that today have probably gained a common belief anyway.
Right. So we did not find any proof for the broken windows theory of crime. So the aspect of it which predicts that visual indicators of disorder lead to more crime, we did not find any support for that. Yes?
I just want to clarify that your results are correlational, not causal.
Yes. Yeah, generally in urban science, it's pretty hard to find sort of causal experiments because it's more complex than some other settings.
Have you encountered any accidental experiments where you have data before and after a specific intervention that a city tried?
So there are a couple of things we are looking at. So one of them is this Green Streets program in New York cities. So what that program does, it builds parks in different neighborhoods, and these parks are built in places where you might have accidental flooding. So the locations are chosen based on this flooding. And so we think that it could be used to look at how urban parks are affecting the appearance of places surrounding it. And the other experiment we're looking at is an experiment on building new subway stations and new streetcars, especially in LA and some other West Coast cities. And their locations are typically not decided based on sort of neighborhoods, based on like variety of different decisions, and so we are hoping that could be one source of data we can use to see how new public infrastructure affects the area surrounding it.
Did you look at the real estate value in comparison to as a data point?
So that's something we are working on right now, and hopefully we'll have some results soon as well.
What kind of computing infrastructure did you need to do all of the analysis on those 100,000 still images?
Oh, well, these can typically run on standard machines with GPUs. Yeah, nothing fancy. Yeah, we probably have like maybe 10 computers with sort of standard GPUs.
So time of day makes a big difference in the prediction of the street score. For example, when everyone's home, then the residential areas will be full of cars, and when everyone's going to work, then the street will be empty, which may look safer, or I don't know which ones.
Right. So unfortunately, most of our data is collected early in the morning when not many people on the street, because that's when street view cars drive. So we can't really we can't really test some of these things. One way would be to use sources like Flickr or so on to collect data which has a timestamp and look at different times of the day. But most of our data just comes from early morning, and we don't really know what time it was collected.
Then the Another question is, have you used this kind of whole tool to try to prescribe something, like suggest some change to the neighborhoods to make it safer with easy changes?
Right. So there's been work from urban planners who look at different urban planning rules and see how that affects perception. And I think that's something that can inform decisions on what urban planning constructs can be used to improve the perception. And the other thing you can do is you can sort of look at the building level data. So you can essentially try to answer a question, which visual elements are affecting perception? And that could be used in an architectural sense, where you can say that this kind of style is more preferred than other, and so on. And I've done some of that work for some architectural companies, and we're trying to sort of dig into that more and see how different elements actually affect perception. Yes?
How much does this depend on the street view setup, as opposed to if you were to take a picture at one of these locations and feed it to your algorithm, would you get a similar score?
Yes, yes. So we have tried that, where we have used data from sources like Flickr, or just manually taking pictures and feeding it to the algorithm, and you can get comparable scores. Yes.
It's very interesting. Did you try to check how much of the improvement were related to real quality of life improvement compared to gentrification of neighborhood?
No, we haven't looked at it, unfortunately, but that's something I think worth pursuing. And we are releasing our data soon publicly, so hopefully other people can also try to study different questions.
All right. Along those lines, is it possible to detect how much of the shift has to do with certain communities being sort of pushed out? So it's hard to tell whether you end up with a city whose growth is actually healthy and positive, or you end up with a city who's simply more segregated,
right,
according to certain metrics.
Right. So some of that is hard to study because we don't yet have demographic data for after 2010. That's very reliable. But we did find that there was sort of not very significant shift in demographic in neighborhoods that had significant positive change in our paper. But that's based on very preliminary data from American Community Survey up to 2013. So as we get more data from census in the future, I think we can answer it better. Yes?
What data on this do you expect to release publicly?
We have been releasing almost all the data publicly so far, and we'll continue to do so. Yeah.
Where is that access?
So if you go to the Streetscore website or even my homepage, you can find links to it.
That seems like a great note to thank our speaker.
Thank you.